That's fine.
Great. So 100 impossibility proofs for distributed computing. This is one of the classic introductory papers in the area. It's written by oh, and people are still showing up. Awesome. Written by an MIT professor who's done, as she mentions throughout the paper, has done a lot of the research herself, and is in fact referring to a lot of her own papers, and kind of tries to bucket the field into sort of 6 general like sub areas: shared memory resource allocation, distributed consensus, shared registers, computing in rings and other networks, and communication protocols, and miscellaneous, which I don't know if that's really a bucket so much as just like everything else. And she has this, and at least I fully agree, idea kind of running throughout the paper that the core idea or thing that you struggle with in distributed systems is the limitations imposed by local knowledge, right? So you only know so much. You can't coordinate fast enough with other people. Even if you've sent them a message or received something, time has moved on, right? So you're always behind, and you don't necessarily know that somebody is even, if the process is still up or if they've received your message. You can make those assumptions, but you're always struggling against this problem. Yeah. And that's pretty much that's the 5-liner on it. Let's dive into some discussion. So what did other people think about this paper, or have questions?
So it was really neat seeing the I think she called it out at the end. There were two limits that came up a bunch. The n, I think it was n greater than 3t, and the omega of n log n. And it I don't know, that seems interesting and feels like there's probably some deeper structural connection there. And I don't know, it seems like I'd suspect that there's probably more work on that because this is a paper from '89, but that seems really neat. I don't know. Oh, and a beginner question, what does quiescence mean in the context of distributed ring networks or whatever that was? Because that it was used in a way that I wasn't quite expecting.
So I haven't seen that term used a ton in modern papers, at least in that way. If I remember correctly, because I also noted that when I was going through the paper, I was like, I think this means resolved or to have come to conclusion for the round, things like that.
Okay, yeah, it's sort of what I figured, but I was unsure if there was a common, it means a specific thing in modern parlance or whatever.
Yeah, my memory of the term is that it is when the distributed network basically achieves a steady state. And with the ring topology in particular, if I remember correctly, it was that you can easily run into situations where one side of the ring believes that it's reached a steady state, but there's still messages that haven't reached it from the other side. And so because of that limitation in local knowledge, you can't really know whether there's still messages coming.
Okay.
John, you have your hand up.
Yeah, I was trying to. Can you hear me?
Yep, you're coming through.
Awesome. Yeah, I was trying to figure out how to do that actually for a while. So a little comment on what Brooklyn said. So yeah, I come a little bit from blockchain implementation background. So for me, the actual not interesting, but the actual completely new bit, or not even completely new bit, but a long forgotten bit was the mutexes and all the low level stuff. And I wanted to say something about what to a little bit expand on what Brooklyn said about how the central idea is that we have knowledge limitation based on time, but in case of this sort of either single CPU or CPUs being very close together. We also have like space limitations. And it's very interesting how this paper kind of, how this field in general ominously unifies those, because people were thinking about this stuff long before, even before Erlang was a thing, right? And Erlang also predated the multi-core and the stuff that they used for time-separated computations, then started being used basically one-to-one in space-separated computations. And another thing that made me think from reading this paper is very often when we write diagrams for protocols, like message passing diagrams, we forget that clocks go at a different rates. And this was like something I didn't think about for a long time. And I was like, oh, right, that thing, I should probably keep track of that. And also, I also have a tiny, not even, well, since I didn't touch distributed systems like hardcore for a while, I kind of started to forget things. But if I remember correctly, many of blockchain systems have interesting properties when they still work in presence of more than third attackers. Like we have, for example, if I remember correctly, Ouroboros, the paper I was working with the closest, I guess, in my professional career, it uses basically kind of, I don't want to say finality because I don't know what it means, but like they use the idea that we will mark information as trustworthy only after a considerable delay as the protocol gets executed. And as far as I understand, they kind of do impossible stuff. And when I was reading the conclusion of this paper, when Professor Lynch is talking about what good do impossibility results actually do for us, she mentions that, well, perhaps it should help us to stop searching for algorithms which are impossible. And this is immediately something that sprung to my mind, is like, well, sometimes under different assumptions and with different problem statements or slightly different problem statements, we actually can achieve the impossible if we try hard enough. So again, I'm also like semi-beginner, so I don't know if it makes sense, but these are my thoughts.
Yeah, I think what you're saying makes sense, and I think she addresses that a little bit too in the paper, where I don't have the exact quote, but she says something about how even if you know a result is possible, if you're able to change the problem statement slightly to introduce some sort of randomness or probabilistic algorithm, you might be able to achieve something that's good enough for your use case, but without breaking the bounds of what you've proven can't be done. And I think that's a really, really important thing to keep in mind as a practitioner. So many of the problems that are actually being deployed for real uses on paper seem intractable. And it's only when you view them through a fuzzier lens that you can actually get work done.
Yeah, or I think in the same section, she also mentions, like, there's the reframing, which is absolutely true. And then there's, does it work well enough enough of the time, right? So like we can weaken the constraint on tolerance, right? Fault tolerance, for example, which is, I think, or even on time. So, Google Spanner uses a time range to say, well, we know that our worst case latency is this many milliseconds. So we just want to accept messages faster than that, right? Right, Ed?
I need to learn how to lower my hand. All right. There. I also thought it was a wonderful aspect of this paper, as well as sort of something of a landscape analysis, where you did really get to see a lot of conversation around the value of impossibility proofs for practitioners and really understanding what is their utility, and in particular where she's mentioning conversations with people who have been shown that they are claiming their system actually is doing something that is on paper impossible, and forcing them to refine their definition of what the system is actually doing, which I found to be a really, really, really useful characteristic of this paper in particular. That, and this, like, her continual sort of gesturing at modalities of thought that would allow us better tools for interrogating our work as practitioners. And so I think she made numerous sort of efforts to show, hey, here's different approaches for doing impossibility proofs, and these are valid for different reasons and in different applications. But also here's really pointing to like why that work is really useful. And personally, I found this like super informative as somebody who does not spend a lot more time in practitioner space, a lot less time thinking about impossibility proofs. But this is like the framing of thought that this sort of gives, and the multiple approaches, like in my mind, like the starts off with like the formalism of this, and like how we can do a formal definition of everything. But then we can also do these with much more scenario driven counterexample style proofs, and the revelation of the inner details of how you even approach that, where you say you just assume the existence of an algorithm that does the thing that you believe should exist, and then play point counterpoint until you get to something that is just not possible, right? And that self-contradictory. I thought it was like super, super useful. And I definitely like, I'm really excited to put that to work while thinking about protocol design. For me, that was like it was really useful, not just to hear that if you do not, like in my mind, going academic has always meant formally model everything, get out the equations, really, write a bunch of really nice doodles that quantify exactly how something works. But this different categories, I was really, really excited to sort of like be given tools for thought. So yeah, I love this as a starting paper. I thought it was really useful, definitely long, but I'm pumped about it.
Yeah, everything you just said absolutely resonates with me. And one of the big things that I took away from this paper was the idea that these impossibility proofs are useful for more than just proving what's impossible, and that they also show up a ton in the design of algorithms and distributed systems and data structures as both a clarifying tool and a way to make implicit assumptions explicit. On the 5th page, there's actually 2 quotes that I really loved. One of them was, it seems to me that the higher level of abstraction of the proof makes much clearer what is really going on. Perhaps there are other impossibility proofs containing explicit constructions of bad executions that could be made more understandable by describing the bad executions implicitly by a simple way of generating them. And then a few sentences later, she says, about a different result, I found this to be an immensely interesting result, but unfortunately I couldn't understand the proof. The main problem with it was that it was not based on a rigorous formal model. And those 2 quotes together really take me back to the value that I get out of techniques like property testing and out of lightweight formal methods techniques like languages like Alloy or TLA Plus and things like that. Usually we think of them as being tools made for and by mathematicians for the sorts of work that Nancy Lynch is doing here. But they show up just in really practical use cases too, purely as a design tool for just making sure you understand a problem and all of the limitations of your solution. And yeah, I just really think that tools like that could find a lot more use in more common engineering than we see today. And I think that's really something she comes to at the end of the paper too, when she just says that impossibility proofs are much easier in our area than in most others. And to me, that feels like a call to action that more people should be thinking about these problems and that it shouldn't be kind of relegated to academia.
Yeah, it also made me appreciate how many more tools we have now, right? And like in every language, and then specialized tools as well, right? Like the obvious one from this area, right, is TLA Plus, but there's just so much that we can do now, and that often isn't used except in like really aerospace and things like that, right? John.
Yeah, I want to be a little bit apologetic about engineers who are not using these tools, given that throughout my career I had to work with both kinds. If you think about it, yeah, of course, like computers aren't like, I don't know, computers are kind of easier, especially back then. They were easier than, modeling like living organisms and stuff. But on the other hand, they are a little bit trickier to think about than just pure mathematical abstractions, right? Because we have to figure out what are the exact, Professor Lynch is talking a lot about the importance of modeling in the beginning of your research, right? To kind of understand what are you doing actually, what are you proving, sorry, actually. And I think that this is a huge kind of roadblock, like one of the roadblocks that people face, that they kind of don't have this, and me including, we don't have this kind of framework in our minds to understand, okay, well, what are the common tools to model what I'm doing with computer systems, and what are the properties that I want to have in computer systems. And of course, for example, in blockchain area is better because we have like the standard properties, we have very high quality research already by now, and it's kind of easier to work there. But like when I'm just making my startup, it's very hard for me to like start thinking formally about it. And another thing is, another thing that stops people is that while we have close to mathematical, like things that are close to mathematical, like, I don't know, very easy to formalize, like stuff like we can do with Agda, for example, they are, again, we can figure out how to do. But when we start working with highly asynchronous systems, we kind of like the power of, for example, Agda and formalisms with Agda, like kind of goes out of the window, because we still have to make this huge bridge between like, like the reality and the model, and it's just kind of too much. And this is why I'm really suggesting people to focus on first formalizing their actual problem domains without kind of thinking too hard about like all this stuff flying all over the place. And then if they are comfortable with it, then to figure out stuff when in asynchronous environments.
Go for it, Philipp.
As someone who's not that familiar with all of the references in the paper, she mentioned something which is, I think, relevant to the discussion about formalizations. She mentions I/O automata. Can anyone explain what exactly, or what's the insight behind that? How's that the basis, or can it be the basis for impossibility proofs?
I have a vague sense about this. I had posted a talk that she had given in the channel, and I kind of feel like this paper, she was exploring ways of sort of laying the groundwork for doing these types of impossibility proofs, and she wanted to provide a more general method where you could make some assumptions to do future proofs with. And in that talk, she shows a I/O automata book that she published, and I think that that's kind of like her system for working on future impossibility proofs.
Brian, could you post, I know that it's in the Discord channel, but just for the people that aren't in there, could you post that in the chat here? So as Brian mentioned, it's her model, or her and her team's model for these things. The really short version, so I haven't studied them in depth, right? But when you read about them, they essentially read like a idealized version of an actor, right? Where you have some internal state, inputs, outputs, and you can send and receive messages, right? A lot of these proofs, proofs in general, right? Or really any formalism, you try to like take things down to their absolute bare bones and have some like abstract version. And so it's an attempt. So even like the ring proofs is, let's forget about all the other stuff that can happen in a real world network. Like, let's just take it down to the part of it that we care about. my understanding of IO automata are that they are this idealized representation of communicating processes in a distributed network, and that just focusing on those parts lets you show, with a pictorial model, really, right? Or like, an easy way of thinking about it. Okay, well, if I'm getting messages like this and they're going out like that, and I have to update my local state, then here's where things will break down, essentially. The Wikipedia article has some, I was just checking it on the side, has some nice pictures in it of the automata.
All right.
Sorry, I meant to raise my hand, but I mean, clapping also is good. So, but in general, I mean, I don't know anything about IO automatons, but in general, as we know from like literature about parsers, I want to like emphasize what Brooklyn just said, how important it is sometimes to, in general, to use kind of state machines to create models for huge problem domains. And then if we have a result, like for example, right, we have language accepting, we have like finite state machines that accept certain words within some language, yeah? And we can then build a whole theory of languages using those things, as Brooklyn said, like as both visual aid and still a mathematical object, which we can then transfer results about from kind of one object to another. And by the way, another kind of idea that I have is that perhaps automata are used here because there were already by then huge amount of results that apply to like automata, so they could perhaps transfer these results from general computer science to their extension.
I guess the irony is the interesting thing about the formalizations for impossibility proofs in distributed systems isn't how the individual actors are working, but instead of like how they work together. So I guess IO automaton to me was kind of weird because, of course, yeah, the individual nodes or whatever are acting like automatons and you can send messages. But then how do those messages get sent from A to B? How do we represent that? Do we always have the same set of automatons, or like that's, I guess, the main questions to me. So maybe it's a little bit weird to call the formalization the IO automaton formalization, because to me it's like more important about how do they work together than what are they. That's not really a question or anything, just I mean a comment, I guess.
But I mean, isn't the core idea, again, absolutely like superficial, isn't the core idea that we don't know and can't know anything aside from what a particular node knows, and kind of this is where the many results stem from? Like literally, if you remember the proof, for example, where she's talking about formalization of like clock synchronization problem, right? For 3 actors in presence of 1 fault, right? This is like literally this idea, right? That we have 2, in this case, groups of 3 nodes. One is really a network of 3 nodes, and one is part of a ring with a gradient of clock speeds. And she says, well, since there is no way for them to distinguish their environment, she builds a contradiction in constructing her scenario. I don't know. So I don't know. I think that we really should go and read the paper where she uses this stuff, because, for example, she was also saying how they weren't sure if they will get any results with this IO automatons at the moment of writing this. Well, some previous paper to this. So I think we should just go and read instead of speculating, maybe.
Well, they did pick up in popularity a ton since this work in '88 or whatever it was. And I think you really got to the core there in response to Philipp's question about us really not knowing anything except for what the node itself can see. And I think a really good analogy here is possibly actually pure functions and functional programming. And something like Haskell, you have a function that is defined entirely in terms of its input and output. And that's essentially what we have with these IO automata. The main difference being that they also have a sort of memory and can keep track of the messages that they've seen before to try to build their own internal understanding of the system, but without being able to reach out to any sort of global state. Because really the fundamental problem that Dr. Lynch is getting at here is that there's no such thing as any sort of consistent global state for a system like this.
And just an observation on top of that, even outside of the paper, is that despite the fact that we can't get a global state that we all agree on, like it's literally not physically possible, right? Big part of this paper. That's what we all want, right? That's all of this distributed ACID database stuff, right? And so we kind of lie to ourselves a little bit, and we're like, well, in these conditions, we get something close enough to it, but it might fail, right? You have lots of people have, myself included, have problems with the CAP theorem, right? Where it's like, well, you can either be partition tolerant or you can just be down, right? When one of them fails. So it's like it's never, it's not something that we can actually get, but it's highly desirable to have. And maybe we should stop making things that claim to do this. I'm not sure.
I'm sorry to interject. I remember when we were working on Ouroboros, on like engineering validation of Ouroboros, we paid a lot of attention to physics. Like, well, sorry, not to physics, but like to the reality of physical world, right? To like what Brooklyn is talking about, for example, in her edge computing talk, like the speed of light stuff, right? And while it's not a big research concern for this paper, we were making sure that for an actual implementation or initial implementation, we were picking the constants that, just for example, make sure that if we need to send a message across the globe, we actually have rounds long enough for it to make sense. And I think that in the end, we actually, if our protocols kind of are slow enough, then we kind of can go around all, like not all, but many of those problems, and at least gain some meaningful message processing within like time periods that our protocols create.
I wonder if it maybe makes sense to do something like calculus style, where like you can't ever actually get to the point, but you can approach it to like an arbitrarily close degree. That seems like maybe a useful way to work around the impossibilities. But I do not know nearly enough about either calculus or distributed systems to know if that's actually a useful way to think about it.
That feels like a little bit what Brooklyn was saying earlier about how Spanner works, where they have these upper bounds on what the latency can be so that they can make guarantees within those intervals.
Yeah,
Or
I think
I thought.
Or it seems related to the randomness she's mentioning in the paper, because like you can say, well, it works in 99.9% of the cases or whatever if you choose the right parameters. So I guess that's a similar way of thinking it about like approaching a kind of limit, right?
Yeah, I just wanted to like call some more attention to your framing, Philip, of like the question of why start with the individuals when we're really trying to end with a end network configuration, right? This question of, colloquially bottom up or top down. And I think it's just really worth considering where you start and how that will dictate where you can end. And the idea that, okay, yeah, we agree that that looked at from a specific, from the bottom up angle, there are parts of this that are just physically not possible. We can't achieve an actual type of consensus. And we're saying, and this course of this conversation, we've sort of, well, okay, can we get within an acceptable bound? Okay, that's exciting and interesting. But like, how do you describe the problem? I always find it so interesting that like we also bring up sort of meat space predisposition to this conversation. Like a lot of this maps really carefully onto individual brains and our desire for a collective understanding of something. And sometimes when we're talking about networks, we actually do have this sort of capacity to step outside of our human metaphor and think a little bit more about, okay, cool, what do we want the network to do, as thinking about it as more of a rhizomatic organism and something that has more of a high level configuration. So Philip, I just think your question really hints at that, and I want to just take a highlighter to it, that like it's a really important part of when we think about these things, because in practice, I think the biggest challenge we run into as practitioners of people building distributed systems are the emergent behaviors, and really how much we tend to come at this problem from the perspective of writing papers and code that tries to execute this from individual machines replicating lots of times, and then we try and like sort of deal with the faults and bad actors in very specific ways and cordon them off. But we don't, what I haven't seen a lot of, and what I'm lately really hungry for, are more top-down tools, more tools that really are attempting to understand what are the emergent behaviors of group action at this scale, what happens, and how does this system change when these numbers change. And we don't really, like, for me, it feels like there aren't meaningful tools for this in the practitioner space, and that approach is it kind of hurts my brain to think about. And that's the thing that I'm like the most interested in understanding, if there are other people who have been exploring that space and thinking more from the top.
There is this person, Greg, okay, I don't remember his name, but he wrote a book called Scale. And an interesting observation that I took out of it is that when we start to think or to do science applied to emergent behaviors, it's very hard to stay within one discipline. And when we're talking about computer networks, and this is actually something that I'm doing a lot for my job, because 99% of my day job right now is making sure that we are making commitments to our customers that we can accomplish, right? So that estimating times for projects, making project plans, etc., etc., etc. So the way I approach it is, well, to sleep well at night, I approach it in a quantifiable way. So I actually do some, I can't call it stats because I don't have training in statistics, but I do some hand waving around like actual artifacts and actual products of us or other computer programmers, and analyze, how they, what is kind of the entirety of the system's life cycle, as systems theory teaches us. And I think that what you are describing can be an emergent approach to quantifying existing artifacts, like logs, like maybe some inspecting like reflection of some running systems, etc. And gladly we have stuff like gladly we as computer systems engineers started thinking about this stuff for a while already, right? The concepts of traceability and the concepts of other like advanced logging are already very widespread, and everyone is running their Grafana servers, like get some pretty graphs and stuff. So I think I think that if we do some interdisciplinary stuff and actually approach it as kind of digital archaeology, then perhaps we will be able to see the big behaviors that you're talking about.
Just to directly address what you were saying earlier, Brendan, I think the closest thing I've seen to the sorts of top-down tooling that you might be talking about, you've probably come across this on your own, is modeling tools like Isabelle. There's been some really exciting work in using Isabelle to model like queues within like newsletter companies and things like that. And basically just trying to get this high-level model of the entire architecture for a company or a system, and see how changing things like the delivery rates or failure rates and so on cause cascading failures. And I don't have basically any firsthand experience with Isabelle, but there's some very good strange loop talks about it.
Also, from a practitioner standpoint, you can use other techniques like data flow, right, to show, okay, well, I'm going to have, these queues coming in, they're going to, here's the incremental back off rate, all this stuff. And so you can get this high level description that then, as you boil that down, eventually to assembly, right, you get more and more detail, but it's this top down from a specification down approach. But that will, by definition, not have emergent behavior, right? Because it's fully captured.
I just realized that I have in my internet journeys encountered a tool from a totally different domain for modeling this sort of thing. It's a game dev tool, and it's called Machinations. And so you like feed it the way that your mechanics work. So like you like, here are the sources of money and sinks of money or whatever, and like you build this whole graph of how the whole system works, and then you can simulate it and see like, oh, oops, hyperinflation, or like, oh, there's actually this doesn't work, or it runs out, or fails to sustain itself, or whatever properties you're looking for. And so I don't know, it seems like a neat relevant tool here in the like modeling complex systems domain.
Looks so much like a circuit emulator.
Oh yeah, definitely.
Brooklyn mentioned data flow, and that brings my mind to traffic engineering, which I think is a field that we can learn a lot from in distributed systems. It started in the early 1900s, primarily as a way of thinking about and designing the telecommunications networks that were starting to be built all across the entire world. And I think that something that's fundamentally different between what we're doing and what they were doing at the time is that we have really quick iteration loops, and the cost of failure is extremely low. So we can build a system, watch it fall over, figure out what happened, and then try to fix it. They didn't have that liberty when they were lining telecom cables between the UK and Switzerland. So if you go through the history of telecommunications, you can find so many formulas from like Little's law, which many of us have probably come across, to like the Erlang loss function for figuring out what the availability of a system is going to be based on the rate of failures and things like that. And these are something I don't see applied very often in this sort of work, but I think that there's a huge opportunity for stealing what's been done before in kind of a more physical domain. Even I'm an Erlang person, and as I build Erlang systems and find ways of addressing the problems and bottlenecks that I run into in my systems, usually when I find a system that finally works, I realize that it's basically a design that I'm stealing from some Swedish person in the 70s.
I think you just described most of computer science.
Yeah, I know you and I have chatted about this.
I'm always shocked whenever I come across a like computer science result that is in use that is like recent. I think the most recent one was there was an innovation in Prolog if stuff like in 2016, and I did not realize that like, so there's lots of that.
The indexing diff paper.
Yes, exactly.
I've been waiting for a good time to mention this, but there hasn't been a good point. Earlier, John said something that I got really excited about. Like right at the beginning, he brought up mutexes, and I loved a quote in this paper right at the start of 226 synchronization. Dr. Lynch says, I am here grouping certain synchronization problems together with consensus problems, since they involve processes agreeing on when to perform actions. And that was like a flash of insight for me because I had never connected those two before. But reading that, it feels kind of obvious that really the main difference between distributed consensus and something like synchronization is the addition of unreliable networks and of the speed of light. And that's something I've never seen talked about anywhere else, but it seems like a really cool unifying idea here.
Yeah, could not agree more. It's actually the bit earlier, right at the very beginning about, this is about working with local knowledge. Is true, like that's the fundamental idea, right? But this messages take time to send and they might be unreliable. And the unreliability is something that's not, she doesn't surface as often, but it's like, yeah, you could drop messages at any time, and that does get talked a little bit about. But
yeah. Actually, I have a quote here from another book. I've been reading Designing Data-Intensive Applications by Martin Kleppmann. Absolutely spectacular book. I highly recommend it. But there's one quote I really loved. He says, if we want to make distributed systems work, we must accept the possibility of partial failure and build fault tolerance mechanisms into the software. In other words, we need to build a reliable system from unreliable components. And that's absolutely the core of what this field is. But I think this paper points to kind of the other side of the sword here. And it shows that impossibility proofs can tell us more about what the limits of the reliability that we can introduce into a system built of unreliable components is. And this comes up again in the shared register section. She mentions that you cannot implement a data object for fully resilient consensus out of one that can't implement fully resilient consensus in a weight-free manner. And yeah, that sort of thing feels like the sort of thing that we should be aware of as we're trying to compose all of these different tools together to make something that is greater than the sum of their parts. There's always going to be limitations to what properties you can get out of a faulty system, and we're working with faulty systems here.
I also wonder how much we can narrow this down from, like, we think distributed systems, we're talking about, the internet, really, right? Like things going over long distance. But we also have multi-core machines that are working on problems together. It's just the distances are much smaller, right? So it's like literally per machine now, we have multiple machines coordinating.
Yeah.
Coordination time isn't zero.
There's also definitely like cosmic rays are a thing that like your hardware, like even inside the processor, your hardware can totally fail on you, and it probably doesn't matter too much like down on Earth, but I'm pretty sure that's a fairly significant concern in like space stuff where there's a lot more radiation going on, and so they actually need to like really care about that a lot.
I saw a talk recently, I'm trying to remember, was it a strange, doesn't really matter, where they measured how frequently bits were getting flipped by cosmic rays at sea level, and it was actually a shocking amount. It was like on the regular, basically.
It's terrifying.
This is a bit of a tangent, but there was a while ago, someone put out a bounty on a Super Mario 64 like speedrun technique where someone was playing, and like there's a VOD of it on Twitch, and they managed to like warp Mario like all the way up to the top of the level, and that was like useful for the sort of speedrun they wanted to do. And I believe it was eventually concluded, like they carefully recreated it using like perfectly accurate like frame by frame inputs, and they eventually confirmed that the reason that Mario warped up to the top of the level was because like a cosmic ray hit the system and like flipped a bit.
It's really interesting how the stuff still is possible, because our computers are like, I mean, I know so many like some people who work in Intel and none of them know how the Intel chips work. But I would assume that they have some sort of like, you know, cosmic ray protection layer or whatever in their like parallelization pipelines.
I mean, there's definitely, I don't know about the processor stuff specifically, but I know that like ECC, like error correcting RAM is a thing. And I don't think it's super common in like desktop machines, but it's way more common in servers as far as I'm aware.
By the way, to conclude the tangent about recent results, the one result that I had to check if it's recent, but it feels recent, is like finger tree data type. It's 2006.
Which part of like that the finger tree exists?
Yeah, I mean they just constructed and analyzed them. Well, I mean, obviously, well, I mean, you can construct any tree accidentally at some point, but like, yeah, that's fairly recent. Yeah.
Yeah, I think if I remember correctly, finger trees are from Okazaki's paper, which is basically the beginning of the entire field of like purely functional data structures. And it's just kind of mind blowing to me that that's barely 15 years old.
Yeah, so that paper, now book, I guess, was a collection of existing techniques and then supplemented with like, well, you know, how far can we take them? So I think finger trees are actually even older than that.
Gotcha.
But like, yeah, like we have to appreciate that we have what, 60, 70 years total, right? With like computers at all, you know? So it's incredible the things we can do already, right?
Mm-hmm. Going back to what you said a moment ago about how we need to be concerned with the travel times of information, even outside of distributed networks. To steal from telecommunications again, like supercomputers, HPC, et cetera, they also rely on like special network topologies to make sure that the different processors and switching networks and so on can transfer information as quickly as possible, even within a single data center or within a single computer. Like so much of the effort that went into like the Cray supercomputer just had to do with the like design of the routing layer between all the chips. And yeah, it's just an easy thing to forget that like data locality and cache locality are that important to us in every application we do with computers. Oh, and I dropped a link to close networks, which is what I was referencing there, which is how these sorts of circuit switching networks are typically designed within data centers and within HPC, and those date back to telecom too. But
awesome. So just a quick time check. We have 5 more scheduled minutes. We can obviously hang out a little bit after as well, but just and any wrapping up thoughts people have?
The focus on like building formal models and using impossibility proofs as a like testing ground for them is really neat. And I sort of wonder both like if it's possible to do a like build a sort of piecemeal like formal model where you can like pull in the pieces that you need for what you're doing and leave out the bits that you don't care about. And also like what is the what is the progress? What has happened since 1989 in the field of formal model stuff?
Unfortunately, that's still an unsolved problem.
Oh no.
Dr. Lynch calls it out in this paper about, so she mentions that one of the hardest parts of producing these formal models was getting the admissibility requirements stripped in terms of making sure that all the processes are making progress at meaningful rates that they can model properly. And that is something that is an integral part of writing TLA plus specifications, for example. And I don't know if any of you follow Hillel Wang. He writes a lot about formal methods, especially lightweight formal methods. And he has an essay I absolutely love called Why Specifications Don't Compose, that is basically about this idea that TLA plus specifications, which are basically the state of the art for this sort of thing right now, they have to keep a property in mind called stutter invariance, which has to do with exactly that notion of progress within a distributed algorithm. And when you try to take different specifications that have to deal with stutter invariance, composing them together, that can lead to a specification that is not itself stutter invariant. And so there's a lot of really manual fine tuning you need to do to get these different building blocks to compose together. And I'm not aware of kind of a silver bullet around that. And non-asynchronous and non-concurrent modeling, there's more tools available, but once you get to the distributed stuff, it's scary.
Yeah, this is something I've noticed in a few fields. You know, often hear security protocols don't compose, for example, right? It's like you may start leaking all kinds of information that one depends on that the other doesn't, and things. Which is frustrating, right? Like we want things to be completely modular, right? And yet.
As far as I understand, there is this notion of universal composability, and or at least like this protocol design kind of subculture of people trying to only use primitives that are guaranteed to compose, which is a very cool thing to do. I'm not sure if it's feasible for concurrent and distributed systems, but certainly something like that is happening in cryptography.
One last thing I really liked from here, near the end, she mentions that she found a lot of success with these proofs, basically playing a game with her colleague, where they would take turns, one of them working on the impossibility proof, one of them working on the implementation, and trying to zero in on kind of the ideal solution. We do that in cybersecurity with blue teams, red teams. We essentially do that with our code when we are running tests against the implementations that we write and try to converge on the correct answer. But I just love that approach, and it's really cool to see it applied here.
Yeah, the coming at it from both directions thing seems like a useful common pattern, like in the super general case. Like it even came up a few times in the stuff we were talking about, like the top down versus bottom up. Like if you can squeeze it from both directions, you can get something. Or the what was it? There was another thing that we were talking about. Oh, that was it. I was reminded when she mentioned the like approaching it from both sides thing of when I was reading through the what is the AGDA book called, Quinn, that we were
Programming Language Foundations in AGDA.
Thank you. They have you doing like equational reasoning proofs, and the way that they suggest that you do it is that you like start with here's what I have and here's what I get to, and you work them both towards the middle with like transformations that you can do, and it all feels very similar.
But also there's a social component, right? Which is when you have a colleague who is sharing a context with you and you speak the same language. It just, yeah. This is why I am a huge proponent of properly structured pair programming, not when just one person is working and the other one is watching, but like if you manage to create a social protocol for yourself and a colleague, which works for you, and you really bounce off each other's ideas, then it boosts productivity. And maybe this is the secret of being a 10x developer.
It's more than additive. Amazing. So that's probably a really good point to end on. It is that was an hour somehow. Thanks to everyone for showing up to the first of these. Next time currently is metastable failures, which is a much shorter paper. If somebody wants to do a different paper, let me know. We can definitely either do that next time or work it into the schedule. And I guess, you know, I'll keep the Zoom room open for another, you know, 10, 15 minutes. But that's the official time, and I'll stop the recording and then we can see what we really think about the paper.
Thanks so much, Brooke.